Good morning, students. Today we are going to start the next section of the unit alcohol, phenol and ether. We have discussed alcohol and phenol. Today we will start ether. Now student, what is ether? We can say that these are the organic compounds which have the functional group ROR dash. They can be also known as the called to be dialkyl derivatives of water, right? So what is ether? They are the organic compound having functional group ROR dash. Where students, the R can be the same or it can be a different. R here is the alkyl group. Here R is alkyl or aryl group. We know the water formula HOH and it is ROR. So we can also name the ether to be dialkyl derivatives of water, right? So ether is an organic compound having the functional group ROR dash. Since they are having the structure similar to that of water, they can be also known to be dialkyl or diaryl derivative of water. Student, the next thing comes is the classification. Students class, ethers can be classified into, first is the symmetrical and the unsymmetrical ether. So first classification is the symmetrical ether or the unsymmetrical ether. So ether will be called to be symmetrical when it has the same alkyl group. For example, if it has CH3O CH3, so it is dimethyl ether, right? Or if we have C2H5O C2H5. So it will be known as the symmetrical ether because across the oxygen we have got the same number of carbon atoms. These are the symmetrical ether. Whereas the example of unsymmetrical ether can be CH3O C2H5, where you can see that there is a difference in the number of the carbon atom across the oxygen. So it is the unsymmetrical ether. Now students, the next classification is on the base. This is the first classification, right? Now second is on the basis of whether it is aliphatic or aromatic. So we have aliphatic ether and second is the aromatic ether, right? So under the aliphatic ether, when the R student, R is alkyl group, that time it will be aliphatic ether, right? So for example, if it again CH3O CH3 or CH2 CH3 CH2O CH2 CH3, they are the aliphatic ether. Now under student aromatic ether, we have it under two heading. The first one, when we have only one aryl group. For example, if it is in this way, C6H5OCH3. Right? In this case, student, we have only one aryl group. Right? So it is aryl alkyl ether. So it is aryl alkyl ether. So that is aromatic ether, only one aromatic ring is there. But if we have diaryl, that means if we have both the R to be the aromatic ring, it is known as the diaryl ether or the aromatic ether. Right? Okay, now this is about the classification. Now student, when we IUPAC naming of ether. Okay, so next comes the nomenclature. So under the nomenclature, student, the first thing is that come the common name. So when we name the ether, student, right, that time we will just because here we are having the two alkyl groups together. So when we are naming it, we will name it alphabetically, right? So alkyl will be named alphabetically. For example, if we have CH3O C2H5, that time it is going to be named as ethyl, methyl, ether, right? This is the common name of it. But if we have to name its IUPAC name, student, so while having the IUPAC name, that time, student, the alkane which has higher alkane, if we say that the higher alkyl group will become the parent compound, right? IUPAC name is in the format alkoxy alkane. That means here it will be for the same compound CH3OC2H5, student, it will be named as methoxyethane, right? So whenever we are writing the IUPAC name of the ether, that time the format is alkoxyalkane and it is been named in such a way that the alkoxy will be of the smaller alkyl group and the alkane suffix will be the higher alkane one. Now students, I have written two compounds on the board. Now okay, so here it is CH3O, CH3, here it is CH3. So we have to name this compound. So we can number it in this way 1, 2, 3, right? So here at the second position we have got this alkoxy, that is the methoxy group. So it will be 2 methoxy propane, right? Similarly, student, if you see here, it is again you can start from 1, 2, 3, or it's 1, 2, 3 or 1, 2, 3. So 1, 2 and 3. Again the higher one is the prop, so it is getting propane. Now here we have the substituent and second is methyl. So it is 2 methyl dash 2 methoxy propane, right? So while naming the IUPAC, you have to follow the order of this, that is in the order of alkoxyalkane, and the alkane will be the alkyl group having the more number of the carbon atom, right? And alkoxy will be the one which will be having the less number of carbon atom. Now students, the isomerism shown by the ether. The first one is the functional isomerism. So we have discussed it in alcohol section also, that the alcohol and ether, they are the functional isomers of one another. So if we are writing CH3O CH3, right, and C2H5OH, these two are the functional isomer of one another, or we can say that for the same number of carbon atom and hydrogen atom, alcohol and ether, they are the functional isomers of one another. Student, next on the metamerism. Now under the metamerism section, students, here across the oxygen atom there will be difference in the number of the carbon atom. For example, let's take this one, CH3, CH2O, CH2, CH3. This is diethyl ether or ethoxyethane. With its metamer will be CH3O, CH2, CH2, CH3. right? So here the number of carbon atom is 2 on each side, and total we are having C4H how many? 5, 6, 7, 3, 10. C4H10. Here also it will be saying 1, 2, 3, 4. C4H how much? 5, 5, 10 and 8. These two are metamers of one another, where the difference is only on the alkyl group. Here we are having ethyl on both sides, and here it is methyl, and here it is propyl. So this will be known as methoxypropane. Here it is ethoxyethane. So this is ethoxyethane, and student, this is methoxypropane. So the isomerism which is shown in ether is two. One is the functional isomerism, and second one, student, is the metamerism. Now students, we will discuss the preparation of ether. So the first one is the acidic dehydration of alcohol. If you remember the chemical property of the alcohol, there we have gone through the acidic dehydration of alcohol, which involve the alkyl as well as the hydroxy group. Student, here also the same thing is there, but there will be a temperature difference, right? So whenever the alcohol, let it be CH3, CH2OH, ethanol, right, it is undergoing the acidic dehydration at a temperature 430 Kelvin, and the acidic dehydration is carried out by sulfuric acid concentrated. That time we will get CH3, CH2O, CH2, CH3. That means we are getting alkoxy alkane, or here it is ethoxyethane. Right? So CH3, CH2OH. Now what is going to be the mechanism which will be followed here? Right? So student, first step is the protonation of alcohol. So it is, if we take it to be ROH, right? This is there, and protonation will take place, student. So H plus will get added where it will be adding here, because here it is the electron rich site here. So it is RO, this is H, this is H, and we are getting it in this way. Right? So this, that means we are getting it as alkyl oxonium ion. Now here let us replace this R with an alkyl group. It will be CH3CH2. So it is OH plus H positive. We get CH3, CH2O. This is H, and this oxygen is getting positive charge. So it is known as, student, as ethyl oxonium ion. Now student, the second step is the we can say the removal of water from here, right? So in this part here there will be removal of H2O will take place. Student, what we are going to get? It is CH3, CH2, this is hydrogen, this is there. And what we will obtain here, we will get CH3, CH2 positive, and this water getting removed. So we are getting a carbocation formed here. Student, the third step is the attack of alcohol on carbocation. So the another alcohol molecule, which is CH3, CH2, this is H plus, this is CH3, CH2 positive. Now here, student, what you will see that if we could have just get this and this reaction together, right? So here you will find that the alcohol molecule is attacking the oxonium ion from the side, right, which is just opposite to the leaving group. right? The leaving group is leaving away from this side. Water is getting removed from this side. It is going to attack the carbocation, that is from the opposite side. So this is going to follow, student, SN2 mechanism, right? So here we will get CH3, CH2. This is there. We are getting positive here on oxygen atom, and this is CH2, CH3. Now the last step, you can easily get it, that is the removal of proton, H plus. So you will get CH3, CH2, this is positive here, this is CH2, CH3, right? Oxygen can't live for a long time for in a trivalent nature. So what will happen, this bond, O dash H bond will break up, right, and formation of CH3, CH2O, CH2, CH3. The proton has removed and we have obtained the ether, right? So the ether formation, student, from acidic dehydration of alcohol follows the SN2 mechanism, right? That is, the attack of the another alcohol molecule will take place on the ethyl oxonium ion. Now what again, where is the ethyl oxonium ion? This is there. This is ethyl oxonium. Oxygen is getting the positive charge here. This is ethyl oxonium ion, OXONIUM, right? This is oxonium, NiUM, oxonium ion, right? And student, you can write the second and the third step together also, right? That will be also correct, right? In this way we can prepare the ether from the acidic dehydration. Yes, students, now next preparation is from haloalkane, and here I want to mention, okay, before this, we have discussed now the preparation of the ether from alcohol by acidic dehydration. Student, it's with only primary alcohol that we can get the ether by the acidic dehydration at 413 Kelvin. If student we take the secondary alcohol, that time student there will be formation of the alkene along with the ether, and if the tertiary alcohol is taken, then only alkene will be the product, we will not get the ether obtained, right? So if we want to prepare the ether, student, that time we will use primary alcohol, right? Okay, now coming to the haloalkane, student, the same likewise story is here also. So when we are preparing the ether from haloalkane, we will prefer it to be a primary alkyl halide or primary haloalkane. Right? Now let me write the reaction. It is RONA plus RX, and it will form ROR plus NaX. Here, student, this process or this reaction is known as the Williamson synthesis, right? So if you have CH3ONA plus CH3Cl, that time the product form will be CH3OCH3 plus NaCl, right? Or if we have CH3CH2ONA plus CH3Cl, we can get unsymmetrical ether CH3CH2O CH3. Right? So by this method, through Williamson synthesis, we can prepare, student, both symmetrical as well as, student, unsymmetrical ether. Right? Now, what happens if we take instead of halide, alkyl halide, primary alkyl halide, student, if we will take the tertiary alkyl halide, that time, student, there will be formation of the alkene, right? It will follow the dehydrohalogenation reaction. So if we have CH3C the tertiary alkyl halide. This is tertiary alkyl halide, right? And let it be CH3ONA. This is alkoxide. Now, if we have tertiary alkyl halide, then this alkoxide ion will be acting as a nucleophile here, and it will be prompting the dehydrohalogenation. It will be acting as a base and will prompt the dehydrohalogenation here. So, dehydrohalogenation reaction will be carried here, students, right? And the product formed will be an alkene, that is CH3CH3 double bond CH2 plus NaCl plus one hydrogen which has been removed from here will be CH3OH, right? And if we have the, instead of tertiary alkyl halide, if we have tertiary alkoxide, right, it will be this one, right? We have tertiary alkoxide and this is CH3Cl here, right? Nothing else, simply this reaction is going to take place and we will get the ether form, right? We are getting this ether, right? So we can either 1, 2, 3 or 1, 2, 3. So second position we have methyl group and the methoxy group. So 2 methyl, 2 methoxy propane. This will be the product, right? So you have to keep in mind, and similarly if a phenyl ring will be there, a benzene ring will be there, student, right? So the benzene ring should be present with the alkoxide, with the, it should be phenoxide, right? It should be phenoxide, and this is CH3Cl. That time the reaction will lead to the formation of the we can say aryl ether, that is O, and this is CH3, right? So we will obtain an ether when we have the sodium phenoxide. But student, if instead of the sodium phenoxide, if we have the chlorobenzene, right, or we have this chlorine linked to the aryl group, that time student, this mechanism will become difficult and it will not lead to the ether formation, right? So these two are the main methods of preparation of ether, right, students? So you have to go through this properly, right? And what are the exceptional cases? Please go through it. Both the preparation have got the exceptional cases. Now in our next class, students, we will discuss the physical properties and the chemical properties of ether. Okay, thank you.